All right, I think people are coming back in, so hopefully everyone's shook their legs out and are ready to tackle one of the most onerous questions in all of astrophysics, which is physics. So go ahead, take it away, Ondrej.
Okay, hello. I wish you a nice morning today, and I'm in charge of Missing Physics 1. So what we will talk about today. I would like to start with a question that is very broad and not very well defined, but is very interesting to me. So in what we have heard so far and what we will hear about more in the coming days, is there some physical effect that is missing in the description that can qualitatively change what we are expecting? And of course, nature has all of the physics, but our description of the nature or our expectations often do not have. So basically, what I'm looking at is this moment of surprise when we realize that we didn't include some very important physical effect. This could be Newton's third law or elastic forces or something else. And just the sheer surprise that the outcome is actually different than what we expected. But on a more serious note, with Julian Krolik and Roger Blanford, we got together and we wrote down a number of topics that could potentially lead to this qualitative change of what we are expecting. So we wrote down quite a lot of things like radiative processes, jets and outflow, 3D, MHD, GR, where does the matter come from, how does the evolution of the binary partners inside affect things, warps, planets, and what to expect from observations in the future. And there are 3 sessions like this, and we decided to split these topics in thirds. So today I will talk about radiative processes, where does the matter come from, and the evolution of binary partners. And then the other topics are indicated here in color. And also I should say that Roger Blanford came here and I would like to pass his message that please people send us or Julian and Roger slides so that we can have some content to base this discussion on. Before I get to things that motivate this discussion, I would like to add or elaborate more on the different perspectives that was already mentioned by Sophie and Selma. So we have for these circumbinary disks, we have situations ranging from planets, stars to black holes. And often in planets and many stars and black holes, there is accretion, but there is this interesting case, which actually is my primary interest, and that's stars that are sitting in the center and that are losing mass. So in terms of this accretion, the matter is falling in from the disk to the binaries in the center, but we can have a star that is losing mass, and somehow this mass gets deposited into a circumbinary disk. And to maybe elaborate a little bit more on the question that I was asking, in these situations when stars are losing mass, this mass loss can be quite substantial. So what was mentioned was common envelope and stellar mergers. And what I'm showing here is a picture that shows as a function of time. So this is in years. And this shows the mass loss rate from the binary as was calculated with MESA. So you can see that in these extreme situations leading to common envelope or stellar mergers, the mass loss rates can reach up to 0.1 solar masses per year. And there is no chance that the companion of the star that's losing mass can accept all of this. So quite likely, most of this mass gets deposited into the surroundings of the binary. And in fact, the circumbinary disk or the near environment of the binary should have few solar masses of material. So I find this quite interesting in comparison to, say, the observed masses of post-AGB stars. The basic questions, I think, for the topic of where does the matter come from, is, I mean, where does it actually come from, right? I mean, in planets, we can have stuff coming from the outside, from the molecular clouds or interstellar medium. But in stars, there is a lot of things that can be happening in the center that are pushing the mass from the center out. I don't know much about the supermassive black holes, but I mean, the gas is part of the galaxy and is coming to the center. And I guess to translate this uncertainty into theoretical work, I would like to know whether the initial or boundary conditions of the simulations that have been shown and will be shown are significantly affected by these processes, and whether this can fundamentally change the outcome. Another thing that I'm responsible for is the evolution of individual components. So what it means is not orbital evolution, but actual evolution of the object that's in the center. So for planets, the central star can evolve as it's approaching main sequence. A star, as it gets old, is also evolving quite fast from AGB to a hot object in the center. And of course, common envelope or merger is way more faster than that. So, you know, are the boundary conditions for our understanding significantly affected? And the final piece that should be discussed in this session is radiative physics or radiative processes, and that has many levels that I try to write down here. So the basic thing, I think, is how can radiation substantially affect the actual dynamics of the material? So for example, can radiation pressure push out the material and overturn accretion into an outflow? Is the thermodynamics of the material important? A lot of the simulations have been done with isothermal or adiabatic equations of state, but will including radiation or ionization processes or molecule formation be important for what's happening in the disk? And question that's related to this is, when we describe these things in a computer, what level of sophistication is necessary for the radiation transport? Like, is it flux limited diffusion or leakage or something better? And of course, in the end, we need to compare theory with observations. So how do we do that? That's also something that's not entirely clear. So on this slide, I summarized all of the questions that I could think of, but I also received contributions to the discussion from 5 people, and I tried to order them in terms of the topics that are here. And I would like to now ask each of the people to say very, very briefly, you know, what their viewpoint on this is. So I would like to start with Sebastian Hennig. Are you there?
Yes, I'm here. Can you hear me?
Yes, we can hear you. Should I show your slides, or do you want to do that yourself?
So can already go to the next slide. Right. So I should quickly just say where this comes from. So with a group of people here in Southampton over the last years, we've been developing 3D radiative hydrodynamic simulations of individual AGNs to essentially simulate a parsec scale environment, what was used to be called a torus. And we included essentially radiation physics in there with a specific goal to be able to simulate radiation pressure, radiation-driven winds on the dusty molecular medium. How we did this is we essentially took an SPH code to be able to resolve, to get enough particles where we need resolution to resolve kind of the optically thin, optically thick transition region in this environment. We included gravity plus self-gravity, hydrodynamics, and then really radiation with a kind of, I wouldn't say infinite, but very, very high resolution frequency grid. We use cloudy for the radiation bit to get ionization physics out, to self-consistently get temperatures, pressures, etc. For our cells. This is not only in thermal equilibrium, but the code can really go out of thermal equilibrium, kind of has to equilibrate over time. It has typical cloudy average chemistry of molecular formation destruction in there. Yes, it's gas and dust. For dust, the important thing is that, as most of you probably know, the effective adding ratio for dust is a factor of 100 or 1,000 lower than for gas. So if you are in an HEN or really binary HEN environment, and you are somewhere of the order of few percent Eddington for your entire system on gas, you essentially look at super Eddington for dust. The modification that we now did for binary in this paper, this was published early this year, so it's Williamson et al. 2022 in monthly notices. I'll pop it later in the chat, just a link. So the modifications that we did is we, of course, all of a sudden had two sources of radiation, not just one, if there are two AGNs in there, but I come back to that in a second, which complicates everything a little bit because our radiative approach is we try to solve it as good as possible and do ray tracing. So from each source to each SPH particle to be sure we exactly trace what's going on. And in order to get all of this together and get a circumbinary disk that has about the mass of the black hole system, we need to scale the simulations in terms of masses, but all the rest essentially was just set up as an HEN. So with a clear scaling law, so that it essentially even the scale simulations give you a supermassive black hole binary. Configuration that we tested essentially in the scale version was corresponding to a semi-major axis of an HN binary at 1.1 parsec semi-major axis, and with a few times 10 to the 6 solar masses for the black holes, and the typical Eddington ratio that you would expect for your garden variety HN of about 5%. And we also tested kind of equal mass and 3-to-1 mass ratio. And next slide, please. So, and I just show one of these example simulations here. There are a few more shown in this first paper that we put out. So this is essentially for the 3-to-1 mass ratio. So we have two black holes in there. The scaling here is in units of semi-major axis. So you see this is 2.5 times 1.1 parsec. So it's roughly a parsec. So the things that we noticed here, well, first of all, is you see that well, these three rows are after 1 orbit, 2 orbits, and 5 orbits. One orbital timescale is roughly 77,000 years, so well, just under 10 to the 5 years. What you see is that quite rapidly, only one of the HN is active anymore, or there's something, you see an accretion disk, or what we call mini torus, because it's actually dusty around one of them. The other one essentially is switched off. And the reason for that is, well, it's combination of the hydrodynamics, but specifically the radiation. So all of those spiral structures, etc., that you may form up in just a non-radiative hydrodynamic, they essentially just get blown away and blown smooth in some ways if you have radiation pressure in there. And more specifically, after about 10 orbital timescales, you have blown out the entire inner part of this circumbinary disk, and you have lost most of your mass. So, which means corresponding to about 500,000 years or so. Sorry, yes, 500,000 years. Most of the mass that has built up in the circumbinary disk, once it started to accrete on the HN, made them active after about 500,000 years. This has disappeared, which essentially would imply the new duty cycle, because you essentially switch off your HN and you have to rebuild the whole structure again. Yes, what you also can see that there's still a little bit of a clumpy structure in this disk, but it's actually not giving you a lot of torque. And if you can just go to the next slide, final slide, where I summarize this. So the key point, essentially take away here, is that radiation will actually change, at least in the dusty gas, molecular gas region, will really significantly change the structure in as much as you don't build up as much spiral structure, and you blow up most of the mass to start with after about 500,000 years, or about 10 orbits. You build up this mini torus. The The thing is, we didn't observe any significant torque that would influence timescales of merging, for example, or orbital evolution. But I should say this is still a little bit subject to further discussion, specifically because we are removing a lot of mass from the CBD. And for us, the next step is essentially trying to refuel itself consistently, and that's what we're currently doing. I think this is also one of these open questions. What we are currently implementing with my new postdoc, Kavli, who is also here, and you can ask him questions about that. Is we try essentially to simulate a normal, well, kind of typical accretion from GMCs in a galactic environment onto the supermassive black hole binary, and essentially refuel the HN so that we can have this duty cycle of about 500,000 years self-consistently going on and off. Right, there are also observables, but this is something for tomorrow evening or afternoon for you.
Okay, thanks a lot, Sebastian. Any quick question to this? Yeah, Dan?
Yeah, just quickly, could you say a little bit more why, if you have the equivalent single black hole case, I assume that doesn't blow out the gas and stop your accretion. So what exactly is happening in the binary case that this happens? Is it due to shocks from the binary torques, or what's the difference here between the single and the binary case that causes halting of your accretion?
So I think there are two. Well, it's not just two effects. There are several ones. So in the same paper, by the way, we also compare it to essentially a single HEN and show essentially that's more stable. I think one of the things that first of all happens is that in the CBD, most of your material is further away, unprotected in a flatter gravitational potential, which means that you're less shielded from the central HEN because you clear out the innermost dense stuff that around the single HEN that would normally protect the stuff that's further away. So essentially you have slightly more effective radiation pressure on your CBD that essentially thaws out a lot of the material. I think this is the primary thing. And then I think the instability, kind of dynamic instability, is just from the binary, help just exacerbate that.
Okay, thanks. I think we should move to or there is more question? No, okay. I think we should move to the next contribution. Or there is a question, yes.
No, a question. I'm next up.
Oh, okay.
Would you mind blowing it up full screen, because
I can try.
It'd be easier to see. Perfect. Thank you so much, Ondrej. Yeah, I didn't make it into a full-blown 3-slide introduction, results, conclusions. So I apologize for that. But I have this neat trick that maybe none of the remote participants can see the pointer. I apologize. So this is a kind of cute result that I will talk more about on Thursday, but I wanted to share it with you here since it's relevant to radiation feedback on the accretion flow. And that is, in many cases, when we look and see a luminous accreting black hole, we sometimes see outflows and jets. And one other cool thing that we see a combination of both non-thermal and thermal emission. What this tells us is that the thermal emission is coming from cool part of the flow. Non-thermal is coming from hot part of the flow that probably upscatters that emission. So we need to have two components, we need to have two-phase medium. And this is a result that shows that this two-phase medium naturally appears. So let's take a look at this top left panel. And this is a zoom out. This is about 50 gravitational radii. That's a little black hole in there. And the right panel is a zoom in of the central region. So you see that's a black hole, and then there is this disk. And this is all density, logarithm of it. Red is density of 1, and blue is density of 10 to the minus 10. So basically it's 0. So we have a disk in the equatorial plane and almost nothing above and below. And these black lines show magnetic field lines. And what's really cool is if we basically start with the radiative disk, and this is disk with radiation transport included through 2-moment scheme, it accretes at 30% of Eddington or so. And you see it's geometrically thin. What's cool is that the magnetic flux accumulating at the center causes the disk to be truncated. So this is thermal emission from here. The disk is thermal and cold. And here we see something messy. And this is a zoom in here. We have dense clumps embedded into hot, what you can call corona. So magnetic field causes the disk to break up into this two-phase medium. And you can see that this is the ion temperature. And whenever you see dense clump, this is a clump, another clump here, they are cold. And everything else around, the protons are hot. And also in the clumps, you see that electrons are the same temperature as the ions, because high density means that the two are coupled to each other through Coulomb collisions. And in the corona, you see the electrons are colder than the ions. Like here, let's say this is a hot region of ions, but low density. And here you see electrons are much colder. They're yellowish instead of red. So this is awesome because we may have finally simulated this corona that we see everywhere in AGN, in X-ray binaries, and we're wondering, what is this? And so it's possible that all we need to do is to flood the central region with magnetic flux, switch on radiation transport, and Coulomb collisions, which decouple things when they are low density and couple things temperature-wise, ions and electrons when they're hot density. You will ask me, what happens without magnetic fields? Here is the answer. If there is no magnetic fields, you see that there are no clumps, and the ions and electrons are at the same exact temperature. So there is no two-phase medium. And as a benefit, we also have powerful jets over here, which are taking away about 50% of rest mass energy. So that's also kind of really cool demonstration that the jets that we see, we're wondering how can luminous disks produce powerful jets? That's a maybe story for a different day, but I also thought I would mention that. So I apologize, this is kind of busy slide, but it's all in one slide. So hopefully that compensates partially for that. Are there any questions?
Was Coulomb scattering the only thermal coupling between electrons and ions, or, okay, so there were no plasma processes or anything like that. So this is the kind of lower bound on the degree of heating to the electrons.
So the we included the reconnection heating that partitions the heating into some heating of electrons and some heating of the ions. So there is direct heating of both electrons and the ions, and there is also additionally coupling through Coulomb collisions, but there is no other type of coupling between ions and electrons that we have included. That's exactly right. Thank you for the question, Julian.
Yeah, I'm just curious if you have any commentary on sort of what sorts of light curves you would get out of this kind of simulation. So what might you expect in terms of optical variability versus X-ray variability and those kinds of things from those clumpy interdisk structures?
Thank you for this awesome question. We haven't yet done any radiation post-processing of this. So ideally, we would do some sort of Monte Carlo radiation transport. We would actually compute the spectra. Here, we cannot quite compute non-thermal spectra because in the two-moment approximation, we assume that everything is actually like at a single, essentially, temperature. Yeah, we can't quite do that, but we can infer what would be the luminosity of different components. The coronal luminosity is interesting. It's around 10-ish%. So it's not 0 and not 100%. Yeah, that's all I can say for the moment. And the other thing is that the temperature of the corona is around 10 to the 9 Kelvin, which is, or like maybe 10 to the 8.5, which is precisely what you are, like if you look at the corona and you infer the temperature of how hot do you think electrons should be to upscatter things, that's exactly what observers infer. Please correct me if I'm misinterpreting the observations, but we were very excited. And there is a range. Yeah, exactly. Good point. The point was a little bit lower, but there is a range between 10 to the 8 and 10 to the 9. And what's also really cool, this is for X-ray binary, but for supermassive black holes, the coronal temperature stays exactly the same, which is what we see. So we're kind of trying to, maybe now this is showing that we are now trying to understand what the physics is based on this sort of 3D simulations.
Oh, hi, this is Zoltan again. Pardon my ignorance, but I always have a picture of the corona, which I think is from reverberation observations, that it's sitting above and below the disk with some structures. Is this, whereas your corona well, looks more complicated and much of it is in the disk? Is that an issue, or is this geometry consistent, you think?
All right, let's give me the last response because we got to move on.
Sure. So it's a mess, as you can see here, right? There is corona in between the clumps. There is corona above and below. So yeah, and that comes back to the question from the back. What would be the radiation properties of this? We don't know yet. And the beauty of this is, I mean, if this is the lamppost, that's whatever nature wants the lamppost to be.
Okay, thank you. We need to move to other contributions. So Hayang, are you there online?
Yes. Yes.
Yeah, please be very brief.
Okay, sure. I'll be very brief. Can you enter the full screen mode? Okay, many thanks. So this is, I'm Haiyong, I'm a senior undergrad at Fudan University. And this is a recent work I did with Professor Xuening Bai and Professor Dong Lai. And so it's, first, this work is a 2D viscous hydro simulation using a CNF plus bus. As you can see, we actually did not resolve the central binary, the 2-minute disk. We only focusing on the outer circumbinary disk. So this is actually a very primitive work on investigating the role of thermodynamics in circumbinary disk, because previously people are using this local isothermal condition as I illustrated in the middle of the slide. So what we did is we had this called dynamical cooling. Basically, the cooling time is inverse proportional to the local capillary velocity. And the only free parameter in our simulation is this beta parameter. And when beta goes larger, essentially your inner disk becomes hotter because your cooling time is gradually increasing, and the heating source is still the same because it's viscous heating, right? So you can see for the upper panel of this picture, this is the morphology with the beta gradually increasing from the upper left to the lower right. And beta equals to 0, go back to the limits of local isothermal. As you can see for the top left panel, this is the classical picture of local isothermal simulation. As you can see, the high density lump rotating around the central cavity. And so you can see as beta gradually increasing from 0 to approximately 1 or 1 to 3 sorts, the inner disk morphology gradually change from asymmetric to symmetric. Say the inner disk becomes circularized because of the hotter inner edge. And if you focus on the accretion variability, there's something interesting because you see at the middle panel of this sub-figure, at first, in the local isothermal simulation, we have 2 kinds of periodicity, with the longer periods equals to 5 times the binary opposite period, and the shorter period equals to 1/2 the binary opposite period. And when beta is gradually increasing to 0.7, you see the long-term periodicity disappear, and this corresponds to the high-density lump in the inner disk is disappearing. And what we have in morphology is actually this only slowly rotating twisted feature, which is quite weird. And if you increase beta a bit further, you have a totally circularized inner disk, and basically your accretion goes to quiescence. And because people are focusing on this final prospect problem, so we wish to have something about the angular momentum transfer. As you can see in the like at the bottom of this figure, this is somehow we gradually change beta, and this is along the x-axis is the value of beta, go back from local isothermal limits to gradually hotter inner disk. And along y-axis is the specific angular momentum transferred from the disk to the binary. So this green vertical, this green horizontal line is actually the threshold whether binary shrink or expand. So you see in this simulation, we gradually increase beta, and the answer is the binary will always be outspiraling because the presence of the circumbinary disk. But you see, as beta increasing, you will see the specific angular momentum is decreasing, then increasing again. Okay, so this is basically the results for simulation, but wish to point out, you can go back to the upper left panel as I highlighted by this purple square. You see this twisted mode is actually quite strange. This is something like spiral, but not that spiral because this is not tightening wound and we did not increase self-gravity. So this is the motivation. So for our next study, please go to the next slide, please. Sorry, I have some disconnect. Okay, thanks. So essentially, perhaps some of you are familiar with the centric mode in CVD is first investigated by Munoz and Liswick back to earlier 2020. So what we did is we add this dynamical cooling to this picture, and we found something very interesting is that this kind of thermal relaxation will essentially twist the modes, which is quite strange. And you can see on the left panel, this is essentially the perturbed density profile after our calculation of this linear eccentricity equation. So the upper left panel is the limits of localized thermal, and the lower right panel is the limits of adiabatic. So you can see in the limits of localized thermal and adiabatic, the eccentric mode, say the perturbed density profile are always aligned. But when you have this kind of dynamical cooling and when this beta value is finite, you will find the mode will be twisted. This is actually a nice correspondence between nonlinear hydrosimulation and linear analysis. And again, in the final remark is that if you calculate the eigenfrequency of this, the rotation, the pattern speed of this eccentricity mode, eccentric mode, you'll find as beta increases, the rotation speed of this pattern is gradually decreasing. But damping is something not that straightforward or monotonic. It will increase at first when beta is something around 1 or 10, and decrease again, go back to the adiabatic limit. So that's basically all. Thanks.
Okay, thanks a lot. How much time do we have?
We have time for is there one or two questions on this? Yeah.
It might be interesting to contrast some of these results with cognate MHD work by Scott Noble. I was looking around to see if he could speak for himself. There you are. Whose device for cooling. Perhaps, Scott, do you want to continue to describe?
Perhaps first, I'm wondering perhaps a magnetic field will have some nonlinear impact on this morphology. Because as you can see, as I show in this slide, the damping for this twisted mode is very strong for finite beta. So I'm wondering perhaps this pattern will not will disappear or say only exist for a very short time for 3D MHD simulation. But that definitely was a comparison.
So it seems like so we use a cooling model that also cools at an orbital rate. It's designed to capture any dissipation that the initial conditions feel. So it cools towards a target entropy. But we essentially get a constant aspect ratio because we start with a constant aspect ratio. So it seems from what I'm seeing in your slides that they're similar, but I mean, I think we need to discuss kind of what, where and when are they different. thermodynamically, but also, how other things can affect the dynamics too.
Thanks. It seems like another great compare and contrast. I think we need to move on, unfortunately. I think we have one or two more people who wanted to share, and I just ask that in the interest of time, these people, we could do quick summaries, and then if there's something that's left over, we also have multiple missing physics sections. So in principle, we can defer if we need to.
Yeah, Roman, can you hear us?
Yes, okay, sure. So I'll just quickly go through this very short presentation, especially since Haiyang to some degree has already covered some of these basics. I was a bit surprised that there is such a coincidence in what we are presenting. So yeah, I mean, I will also be focusing on the role of cooling, role of thermodynamics on the dynamics of the circumbinary disks. As you can see in this top figure, which I stole from McFadden and Milosavljevic, one thing that binary does in a disk, it actually launches these beautiful density waves in a disk. And then these density waves propagate through the disk, they carry angular momentum, they carry energy. And when they dissipate, which can happen through nonlinear processes, basically waves turning into shocks and dumping their angular momentum in the disk, or it could be happening due to some linear processes, for example, viscosity or radiation damping. So only when that happens, do the waves affect the state of the disk and start pushing the gas away and forming the cavity. So basically understanding how these waves propagate through the disk and dissipate is something that decides to us what we see in a bottom figure, which is kind of the shape of the cavity. So obviously it's very important to understand how that happens. And what I wanted to do is just to raise awareness to the recent kind of series of studies which we did with Ryan Miranda, where we applied, when we looked at the role of thermodynamics in propagation of density waves in the context of protoplanetary disks, where we found some very interesting things. And then I think that a very similar impact would be happening also in the circumbinary disks. So the bottom line is, we find that in adiabatic disks, which is sort of a pretty classical equation of state, your density wave is propagating, preserving its angular momentum, which is nice and easy to understand. However, the majority of simulations of disks that people do, like probably 99.9% or something, well, maybe not so many, but still a good share, are using local isothermal equation of state, where you prescribe some temperature profile. And in that case, you can show, and we have demonstrated this using linear theory, that you are not preserving angular momentum flux of the density waves. In fact, there is a continuous exchange of the angular momentum due to the nature of the equation of state with the disk, which causes the angular momentum flux carried by the waves to scale linearly effectively with the temperature of the disk. Okay, so in a circumbinary disk, that would imply that if the temperature is decaying naturally, so for example, if you assume the disk with h over r equal to constant, that means that temperature decaying is 1 over r, your angular momentum flux will just be decaying due to this effect, due to this kind of artificial property of the local isothermal equation of state. And I believe that this modified damping of the angular momentum initially injected by the binary into the waves, so this modified kind of spreading of the angular momentum through the disk might affect the properties of these cavities and might actually impact some of the effects that Haiyang is seeing in his simulations. Now, to illustrate these statements, if we go back, to the next slide very quickly, I just wanted to show our results for the sort of the angle. So these plots are a bit complicated, but what they are trying to demonstrate is on the left, in the left columns, we have disks which have been simulated numerically and calculated using linear theory, using local isothermal equation of state. On the right, we are using adiabatic equation of state in which we set gamma equal to 1.001. So very close to isothermal equation of state, but we are properly evolving the energy in this case. And what you can see is that in the low mass cases, when the things should be close to linear, the angular momentum in the adiabatic case on the right is indeed very well conserved. For example, in the inner disk, you can see it plateaus very nicely. But in the inner, in the left panel, for example, if you focus on the left lower panel, that corresponds to a constant h over r disk. you can see that, for example, outside of the orbit of the planet, angular momentum just drops very precipitously. Inside of the orbit of the planet, it grows dramatically. So there is an exchange, this artificial exchange of angular momentum between the wave and the disk. So for circumbinary disk, the outer part of the disk in this calculation, what you find, the decay of angular momentum flux is what is going to be basically happening. And that is something that, one has to take into account when constructing these simulations. And keep in mind that, local isothermal equation of state has this funny property. Now, if we go to the next stage, next slide. So there I'll just show some results of simulations using this constant beta that Ha-Yang has mentioned. And just, basically, it's probably enough to look at the left panel only, where I'm showing, just plotting the snapshots of the surface density perturbation. Again, this is, a planetary case, but it would be similar in the circumbinary case. What you should pay attention to is that different columns correspond to different cooling times. And you can see that when the cooling time is of order 10 to the minus 1 or 1, then the wave actually washes out very quickly as it propagates away from the perturber. That's because radiative damping becomes very, very strong, and the wave just, offloads all the angular momentum flux it carries very close to its excitation side. In a circumbinary context, I think that would imply that the edge of the cavity would be sharper than in other cases. For example, the case of the adiabatic equation of state, effectively when beta is very high, of order 100, in which case the wave propagates, preserving its angular momentum flux. And just one last point I wanted also to mention is that the transition to the locally isothermal behavior, as you can see from this plot, is happening somewhere around or even below this cooling time of 10 to the minus 2. So if you want your, which is very short, it's 1% of the local orbital time scale. So if you want to make sure that your local isothermal simulation is reproducing the true physics, you need to make sure that the actual physical cooling time of the disk, sort of in the inner part of the disk, is actually as short as 1% of the local dynamical time. And whether this is true or not depends obviously on the problem at hand. Anyway, so my bottom line is that, disk thermodynamics is very important. Please be very careful when trying to treat it. I've been beating this drum for a while already, and people in protoplanetary community listen. I think in circumbinary disk community modeling, that is also quite a serious issue. Thank you.
Thanks, Roman. I guess maybe one question.
We have a question, and then we have a comment before we move on. Any questions? Okay.
Oh, I think I heard that. Hi. I just wanted to say that this is a very good point about the thermodynamics. We did a crude. Alex Dittman and I did a crude check of this in some of our work, where we did a globally isothermal simulation with no cooling at all, with where we didn't allow for the sound speed to have any gradients, and there we found that at least the for 2D viscous aligned binaries, that the binary evolution didn't change too much so long as everything was normalized to the sound speed at the cavity wall. But of course, it would be better to do this with proper cooling.
Right. Yeah, I would agree with that. This was a binary, equal mass binary.
Yes. Yeah. Equal mass binary.
So there is this point that, when you have an equal mass binary, then you tend to excite pretty strong spiral density waves in a disk. In this case, nonlinear dissipation may be much stronger than this radiative damping than is present in these calculations. And so radiative damping might be playing some role, but nonlinear dissipation would just completely cut off the angular momentum flux anyway. So there is a intricate interplay between the nonlinearity, the effects of nonlinear damping, and this linear radiative damping. But in any case, just to be safe, to play safe, I would always encourage everyone to think about, at least estimating, in terms of beta cooling, what is the characteristic cooling time, and sticking it into the energy equation. I don't think it's much more numerically complicated to use a simple beta cooling with physically motivated value than to run a local isothermal equation. Sorry, simulation.
Okay, thank you, Caitlin.
Okay. I would have been speaking for a couple of minutes explaining about post-processing system to translate the data from detailed MHD simulations to credible, specific predictions of output spectra using actual radiation mechanisms and radiation transfer solutions, but we've run out of time. So this will be the beginning of my discussion section tomorrow, and I hope that it will be amplified by contributions people send me, because at the moment I've actually received none at all. And surely there are people with their own ideas about physics missing from the topics that I'll be discussing. And the one other thing I'll say is that this method, as it's been applied to single black hole simulations, has found coronae generating phenomenologically similar hard X-ray spectra to what's observed without large amounts of magnetic flux at all.
All right, thanks. Well, thanks, Ondrej, for moderating that. Thank you to all the contributors. That was really great. And thanks to all of you for participating. We have a little bit late, but we have lunch now in the courtyard, and we will meet back here at 2 p.m. sharp.